Alright, for the pre-lecture for today, we're going to be talking about entropy. This is chapter 2 of the textbook. So in the textbook, I think section 2.1 is a kind of nice introduction to this, so that's worth reading through. Section 2.2, if you want to, you can read through that if you find that helpful. I think it's sort of confusing how it's written, so I don't think that that's the best source for this. I posted another source with the pre-lecture notes, so you can see if that's more clear to you, but they do use slightly different notation than we use. They use p of x, little p of x. That means the probability that the random variable x equals the value x. So watch out for that in that source. Starting with uncertainty, the idea here is that a fair coin has more uncertainty than a coin that comes up heads 3/4 of the time, because we can be pretty sure that the second coin will come up heads. Whereas with a fair coin, we really don't have a good guess of what that's going to come up, since both possibilities are equally likely. There's a lot of uncertainty there. If one of the possibilities is more likely, then we have some idea of what's going to happen, so there's less uncertainty there. So where we have more uniform probabilities, where like a bunch of different possibilities are equally likely or close to equally likely, that means the outcome is going to be more uncertain. Whereas if it's like really heavily skewed, where one thing is much more likely than everything else, that's going to be less uncertain. And then for information, we say that a relatively unlikely event carries more information than a likely event. So this probably seems a little strange, but this makes sense because if we know the sum of two die rolls is 2, so this has a probability of 1/36, we know that they are 1 and 1, because that's the only outcome where that event happens. Whereas if we know that the sum of two die rolls is 7, and that outcome, or that value has probability 1/6, then the rules could be 1/6, 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. So knowing that the sum of the two die rolls is 2 carries more information than knowing the sum of the die rolls is 7. So this is why we have this idea that unlikely events carry more information, because then we can narrow down what's happening more. Whereas if a likely event happens, then it's sort of like there are all these different possibilities and we don't know which one it's going to be. For entropy, entropy gives us a measure of the uncertainty of a random variable. It's defined by this formula. So we denote it h of x, and then take minus the sum over all possible values x of the random variable x, and the things that we are adding up are the probability that big X equals little x times log base 2 of the probability that big X equals little x. And the units for entropy are bits. So all of our outputs are going to have the unit, or all of our results for this h of x are going to have the unit bits, as long as I remember to write it, which I might forget. So let's look at an example of computing entropies for some random variables. So let's flip a fair coin once, so x is the number of heads here, so it might seem like kind of a silly random variable, but we'll look at it here. So the possible values for this one are 0 and 1. There can be 0 or 1 heads in a single coin flip. So then when we're looking at h of x, we're going to look at those probabilities, or those possible values, and look at their probabilities. So when we're looking at x equals 0, the probability that we have 0 heads, that happens if we flip tails, so that is probability 1/2. So we've got 1/2 log base 2 of 1/2. And then plus, now we look at where big X equals 1, and that is when we've got 1 heads, so that has probability 1/2. So we've got 1/2 log base 2 of 1/2. So remembering our logarithms, we've got minus 1/2 minus 1/2, so this works out to be an entropy of 1 bit there. Now if we flip a coin with probability of heads 3/4, X is the number of heads again, but now the probabilities are different. So our values are still going to be 0 or 1, but now their probabilities are different, so looking at when X equals 0, now if heads has probability 3/4, then getting 0 heads, that has probability 1/4, so we've got 1/4 log base 2 of 1/4 plus, and then for the probability, or looking at when X equals 1, that's going to be when we get 1 head, so that has probability 3/4, so we've got 3/4 log base 2 of 3/4. So if you work this out, this comes out to about 0.81128 bits. So we can see that the entropy for this random variable is smaller than the entropy for the first example that we did, which is consistent with what we said about uncertainty for a fair coin versus a weighted coin. So we've got more entropy when the probabilities of the outcomes are more uniform, or in this case, when they're equal. So now let's look at a slightly more interesting example where we flip a fair coin twice, and X is once again the number of heads. So our possible values here are 0, 1, and 2. So we can have 0, 1, or 2 heads in 2 coin flips. So now figuring out our entropy, we've got minus, now looking first at X equals 0. So that means we've got tails, tails, which happens with probability 1/4. So we've got 1/4 log base 2 of 1/4. Now looking at when X equals 1, well, the ways that can happen is heads, tails, or tails, heads. So that is probability 1/2. We've got 1/2 log base 2 of 1/2. And then finally for X equals 2, that means we've got heads, heads, so that is probability 1/4. We've got 1/4 log base 2 of 1/4. So working that out, this is going to come out to 3/2 bits. So notice that the values of the random variable X, what the outputs are, doesn't actually matter for the entropy, it's just the different probabilities. So all that matters for this is the probability that each value occurs, and sort of how equal or unequal those probabilities are. So this formula might seem kind of strange or unnatural or like it's coming from nowhere. It actually turns out that for the kinds of properties that we want to be true for entropy, that this is the only way that it can be defined. So that's something that's covered in the book. You can take a look at that if you want. It's a pretty cool result, but for our purposes, knowing what entropy means and knowing how to compute it, that should suffice. So we've got another type of entropy that we can talk about. If we've got 2 random variables, X and Y, we can talk about their joint entropy, so their entropy when we consider them together. So we look at all possible pairs of values of X and Y, and for each pair, look at the probability that those values happen together, and then do the probability log base 2 of the probability, similar to how we were doing with just a single random variable. So if we're looking at a fair coin flipped once, and x is the number of heads and y is the number of tails, then our possible pairs are 0, 0, 1, 0, 0, 1, and 1, 1. Figuring out the probability that each of these has. The probability that we've got 0 heads and 0 tails in one coin flip, that has probability 0. Getting 1 heads and 0 tails in a single coin flip, that is probability 1/2. Getting 0 heads and 1 tails, that is probability 1/2. And getting both 1 heads and 1 tails in a single coin flip, that's impossible, so that has probability 0. So then we add up minus, so we got 0 log base 2 of 0 plus 1/2 log base 2 of 1/2 plus 1/2 log base 2 of 1/2 plus 0 times log base 2 of 0. Of course, we could just omit those 0 terms there. So this works out to be 5.1699 bits. So it's really a similar computation to what we did for a single random variable, except now instead of looking at just the values of that one variable, we're looking at instead pairs of values of the 2 random variables and the probability that that pair happens, so that the value for x happens at the same time as the value of y. If we looked at this was silly. I wrote down the wrong value here. Shoot.